Hey everybody, Daniel here from Basement Tech. Well, I think it's about time to move on from the Python code. I wanted to do one kind of quick video with just a tour of the software that runs on the remote data collection unit. That I wrote in C, just because I'm comfortable with it. You might remember from the hardware video, it kind of looks like this. I'm not going to go through the components in this video, but you can refer back to the prior video where I did do that. So listen, here's the software right in front of you. I'm going to talk about this, which anybody who's done Arduino stuff recognizes the Arduino IDE. I'll talk about this first, but then I want to relate it back to the Python code that you see peeking out from behind. I'm going to talk sort of block, sections of the software without going into too much detail so I can finish this in a reasonable amount of time. Let's just start right at the top. And this gives you a really good idea of the kind of things you're going to find in here. I am going to get into the software and continue the fun, but before I do that I want to pause for kind of a serious caution. This project contains a sensor which will sense carbon monoxide and propane and other combustible gases. But please do not take that to imply that you should be using this project or this sensor or anything to do with the Basement Tech channel to make health and safety decisions. This is a hobby project. These are just ideas put out there for the purpose of learning and hobbies only, and I make no implication or warranty or even the slightest hint of an indication that you should be using this project for safety purposes. So with that out of the way, let's move on to the fun. Alright, let's get into the software. You might recognize right in front of you is the Arduino IDE. I am using this with my ESP-8266 module that I got from Adafruit. There's just a plug-in that makes it work for that, and then you'll feel like you're just programming an Arduino. Right at the top you see all the hash or £sign includes, and that gives you a really good idea of the blocks of stuff that are contained in the program here. Written in C, and again, as I said, utilizing the Arduino IDE. It does have Wi-Fi, so you see the ESP-8266 Wi-Fi included. That provides Wi-Fi. We are using, as I said in some other videos, MQTT, the Mosquito Data Broker, and that's what this pub/sub client is all about. I have talked, I think, before about the fact that I'm syncing up with a NTP, a Network Time Protocol server, so that I can send calibrated time along with each of the data samples. And finally, the sensors that are connected, the Adafruit temperature and humidity. This is the A to D. Remember, the gas sensor is analog, so it doesn't really have any software. Its signal is acquired through this A to D module, also from Adafruit. I like to describe the hardware, very overtly, very clearly. So I list out all of the pins that could be used, and then just uncomment the ones that I am using. In this case, there is just one. It lights up an LED to indicate when a successful Wi-Fi connection has been made. As I started to get into the next phase of development with this board, I needed a little bit of a development environment, so I put in some if-defs around some code, depending on whether the hardware is present or not, and that's what you see here. I'm going to jump to the bottom in just a second, as I like to do, start with the while loop essentially and work my way back up. But remember, while we're here, I am using MQTT, I'm using a Mosquito Data Broker, and each data element needs to have a topic, and that's what you see listed here. Any of you who might have looked at this code in the past, remember there was in the past just a single gas parameter, but I've broken that out into carbon monoxide and propane data values that have behind them my attempt to convert the electrical signals to parts per million. Again, no implication that it's calibrated, no implication that you should be using this for safety reasons, but I wanted to have a more real world sort of natural units parameter instead of just A to D counts. So that's what you have there. Let's jump all the way to the bottom and then work our way back up. As always, and like I talked about with the Python code, I like the loops to be very easy to read. When you finally get to the bottom, it should be pretty easy to read. And that's what we have here. I do connect to the Wi-Fi, and I'll show you that program coming up, but I think it's important for the Wi-Fi connection to be maintained in a very regular basis. So each time through the loop, the first thing is say, hey, is the Wi-Fi still connected? If not, attempt to connect to it. I'll show you that function up above that does that, but that's this section. Sync up with the NTP client. Now the NTP client runs on its own clock. So this update is essentially saying, if it's time, do the update. And that's not very often because, frankly, once you're synced up, the clock that's the time base that's inside the processor does a pretty good job. But I think I had it set to sync up about once per hour or something along those lines. So make sure Wi-Fi is connected. Go read the raw sensors, and then send that data using MQTT. Make sure it's connected before you attempt to send, and send the data. Now, I made a decision at the beginning, and I'm still wrestling with it. I'm sending the parameter data as a JSON string. I think that's probably a good idea and makes this project a little bit more generically useful, but I just find myself decoding it and using it anyway. But I think I'll leave that in for now. So this string manipulation forms up the JSON string for each of the parameters that you would imagine. So let's form up temp and publish that using the MQTT publish. Let's form up the raw A to D gas value and send that out. Then let's convert that raw A to D reading to, again, my attempt with my guess at the math. I'll show you that in a minute. But send parts per million as if the sensor was sensing carbon monoxide, and do the same with propane, convert it as if it was propane. Remember, with this sensor you get one analog value. The sensor doesn't know which gas is causing that that fluctuation or reading on the gas sensor. So what I'm doing is publishing both values, and you can take that to mean if it's carbon monoxide, here's the reading. If it's propane, here's the reading. Good news is, if I set up separate limits in the Python code, which I'll come to in a minute, then I can alarm on those separately, and it turns out they're pretty compatible in terms of ranges, so that's pretty cool. Finally, read the time from the NTP client and send that out. That's really it. One last thing I do at the end, as important as it is to have the Wi-Fi connection, it's very important also to make sure that the connection to the MQTT broker is maintained. So that's this last thing. Go attempt to make sure the broker is connected as well. Alright, well, about halfway through this video I was looking through my to-do list and saw an item that said distribute timestamp to all of the parameters. And so I kind of put the video on hold and went over there and started working on it, and the result is actually some new code for the ESP that you're seeing in front of you here. I really decided to do it the right way. I could have distributed the timestamp up on the Python code, but I really want this this little remote module to be generally useful outside of this application, so I decided to do it right. You saw before that I was using JSON to just send a single value with a key, with a label. I decided the best thing to do is to actually just send the timestamp along with it. Of course, that's the right design decision, and so that's what I decided to do. And why not send a location, so if I end up with multiple sensors I can do something with that too. So what you see in front of you is that code now, where instead of just building up that single parameter string in JSON, I wrote this little helper, I guess it's called, maybe, to just format up a few different things now into a JSON string and send that with each sample. I'm going to slide up. I could have found some JSON library and everything, but since this is so simple, I decided just to write it myself. So I'll slide up here and find that little thing and show it to you, but you can imagine what it is, just some string concatenation to make up a JSON string with some curly brackets and quoted labels, keys, and values. This really is, I suppose, C++, not just C, so I overloaded this function to accommodate different types, literally different variable types in this application. So there's some that are float, some that are strings, etc. So back down here to the while loop, this really makes it, again, one notch cooler. Here we're back down into the while loop, and you see, well, just build up the JSON string and burp it out using MQTT to the Mosquito data broker. Then it was like, shoot, now the fundamental format has changed, so I have to go change all of the downstream things. So this is also where it just gets so cool when you stick to standard things and you have kind of well-constructed applications versus kind of hacked together. So let's put this Arduino code on hold for a second and take a look at NodeRed. Remember, NodeRed is the application that connects really easily to the Mosquito data broker and gives you a graphical way to stitch together the signal paths, if you will, the data flow, and turn it into these things that you're used to seeing me show you, like these graphs here. So, okay, what did it mean to accommodate that change that I made in the Arduino code? Now every JSON packet is different. But the good news is, because everybody knows what JSON is, this was a kind of a trivial change. So let's take temperature. This is a standard NodeRed, I can't remember what they're called, I'll call it a module, that accepts, connects to a Mosquito data broker, MQTT data broker in. That signal flows into this standard module, again from NodeRed, a JSON interpreter, JSON decoder, I suppose, and that turns the JSON into a JavaScript that downstream graphical elements like the graph here can understand. So what did that mean? JSON, I didn't change anything. JSON in, JavaScript out. So I'm not a JavaScript out expert, but now I have two levels of two layers, if you will, in my Java, in my JSON packet. But all I actually had to do, it's just so comically easy, and it just makes me smile every time I think about it. It used to say payload.temp. Now all I had to do is payload.temp.value, and everything worked. And I just replicated that across the other things that needed to change. Let me bring that Arduino code back and show you, what I did. So I send in a string like temp just to label the JSON, to kind of make the JSON self-descripting, if you will, or self-describing, and then the value, the location, the timestamp, and that's all just in this string that gets sent down, decoded by the JSON decoder and understood by JavaScript. Bottom line, it took me less time to actually do it than it did to describe it to you. So I'm really pretty excited about how simple that is. The second downstream element is the Python code. So what had to change there? Let me show you that. So first, remember, in the Python code there are two files. One is this one, which is called monitoring parameters, and I described in way too much detail in prior videos this this class that has all of the parameters in it. And you remember over here, this says, is this packet that I'm getting from the broker, here see I'm subscribed to the broker using this topic, is the packet I'm getting JSON encoded? And based on that flag, then I go in and either decode or not decode. So let me bring over now the main program, if you will, and just slide down here. Let's see, here it is. So remember, messages that are incoming from the Mosquito data broker into the Python code are event driven. When somebody publishes something to the Mosquito data broker that I have subscribed to, this callback gets called on message, and what I have to do is decode it. So I'm going to make this a really short description, but you can see here, if the parameter that I'm interested in has the yes I'm a JSON packet equal to true, do the JSON decoding. I am using a JSON library here, so take the string that's sent, and load S does the decoding and turns it from a JSON string into a Python dictionary. Then I can just refer to the dictionary elements like I would any other Python dictionary. Now I'm playing one little trick here. I want this code to be completely generic and event driven, so I don't know what parameter I'm getting in. So how am I going to figure that out? The JSON, because it has just one top level, turns into a dictionary with just one top level. And Googling around, folks said, hey, just do this thing, and it'll tell you what the highest level dictionary label is, and it works. So alright, sliding all the way back up to the top, I just want to fill in a few of the details behind some of those calls you saw down below in the main loop. What I had for the gas sensor was this data sheet, and you see, I can't do it backwards here, you see a little plot of how the parts per million varies with respect to the resistance of the sensor and therefore the voltage that the A to D sees. That's a log scale, in case you couldn't see it in that very tiny thing, in that little tiny picture. And so I had to go all the way back to some high school math and figure out how do you write a formula for a straight line on a log scale. I think I did that successfully here. If anybody is brave and really wants to dive in and kind of check some of my math, I absolutely would welcome that, and please provide comments in the comment section. But this function, which says convert gas voltage to parts per million, does so with several paths. One is just convert the bits to a straight up voltage. The other is if it was propane causing the challenge, causing the reading, do that calculation, which is a different graph, a different little subgraph on that one I showed you. And similarly, if it was carbon monoxide, do that calculation. I'd love for some math wizard to take a look at this and let me know if it makes some sense. So that's that conversion from voltage or A to D reading to parts per million that I showed you down below. This section here just sets up all of the clients, all of the classes, the instantiations of the classes, for the pound sign includes that I showed you up above. Get the time client going, get the connection to the MQTT thing going, set up the temperature and humidity sensor, set up the A to D, and that's about all we have going on there. I created this little local Wi-Fi connection function just to provide retry in the case that Wi-Fi is lost. It actually seems to do a pretty good job. The power down at the shop is pretty sketchy, and we've had cases where the Wi-Fi has dropped out, and the Pi resets itself when the Wi-Fi drops out, and this little Arduino-like board does a pretty good job of reconnecting. And you notice there's just two paths through here, one to initially connect, and that's when first is true, and one to attempt to reconnect when first is false. Similarly, the MQTT connect has the same two paths through there based on whether it was the first time in or whether I'm reconnecting, and I just make calls down here to the MQTT.connect from the class that's instantiated up above, and that all works out great. Kind of skip this section here. I'm working on trying to find a way to configure this software on the fly, but that's not working yet. Finally, I come down here and I set up the pin for the Wi-Fi, and that's really about it. So let me just kind of conclude here. You can look at this software and understand it as well as I can, but a couple of themes emerged. most of the vendors for the hardware provide just great libraries, and I highly recommend taking advantage of those. There are also tons of examples with anything that you pull into this Arduino IDE, so there's very little research needed to get some of these great little modules from Adafruit and others up and running really quickly. This code primarily provides the function of stitching those various pieces together, providing a little bit of logic on top of it, like the retries, for example, but stitching those libraries together in a way that A, compiles, but B, works. So we're in a really cool time right now where there is so much out there in the maker sphere to allow us to do this kind of really cool stuff really quickly and easily. So let's collaborate via the comment section for this video and all of the others, and keep your comments and questions coming. Lastly, I'll be posting this file up to the GitHub repository, and I haven't done that yet because I wanted to take the chance to give that stern warning that I gave at the beginning of the video to do not use this for safety reasons. So there you have it. This was a blast, stitching this stuff together, and it worked out just really well to provide exactly the functionality that I was looking for. If you like this video, please give it a thumbs up. If you really like it and want to see more like it, please subscribe. Finally, put your comments at the bottom. Ask your questions and put your comments at the bottom, and I'd really much appreciate that dialogue.